Good evening. So in this little video, I'd like to show you a couple things. One of them has to do with inverses. I'd like to just show you why this method they showed you in the book for inverses actually works and tie it in with linear transformations. And the other thing is to take a look at some probability matrices and how they work. And we'll spend a little time with the probability matrices. They're kind of fun. And they're important too. But anyway, let's take a look at inverses first. And let's divvy up the board into transformation land, where we're dealing with functions and equations, and matrix land, where we're dealing with arithmetic. Arithmetic is always easier to deal with. And the question I'd like to answer or talk about in both of them is this. When is there an inverse? When is there an inverse? So in matrix land, when does a matrix have an inverse? In transformation land, when does a transformation have an inverse? Let's begin here. In transformation land, if you have a linear transformation from one space to another, there is no inverse unless n equals m. So let's put conditions here. So n equals m is a condition for having an inverse. And the second condition is, for having an inverse, is L is 1-to-1 and onto. Now, for linear transformations, 1-to-1 and onto are the same when n equals m. That's part of our unifying theorem. So 1-to-1 and onto for transformation, along with n equal m. And those same conditions over here look a little different, but they're the same. The first one is that the matrix M is squared. That's what it says. That's what it means for n to equal m, is the number of rows equals the number of columns. And secondly, 1-to-1 and onto says that the columns of m are linearly independent. The columns are not independent, then the function is not 1-to-1 and onto. So this is the situation when we're looking for an inverse. And if these are satisfied, then the matrix does have an inverse. So let's erase this and give an example. So does this matrix M, 1, 2, 3, 4, does this have an inverse? Or does the corresponding linear transformation, of which this is a representation, have an inverse? And we can answer yes, it's square. Condition 1 is satisfied. The columns are not multiples, so they are linearly independent. If there were 3, there'd be more to check. This matrix will row reduce to the identity matrix, so the answer is yes. Bringing up the question is, okay, what is it? And it's interesting that we have the techniques to solve that right away. And that's part of what I wanted to show you. So we'll again deal with this matrix. But I'm going to go back to transformation land again and look at what it means to be an inverse. it means if L and L inverse are inverses, it means L, if you take first L of X, so you transform X, and after that, you transform the inverse, you're right back to X. So inverse means that whatever L does, L inverse undoes. So if L is tying your shoes, L inverse is untying your shoes. And this works both ways. If you transform a vector with L inverse, and then do L to that, this is again where you started. So if you start with X and you do both of these, you're right back to where you started. That's what it means to be the inverse. L and L inverse undo one another. Over here in matrix land, we know what this stuff is. Well, I'll write what this little circle means. This means, first of all, you do L of X, and then after that, you do L inverse of that. So the little circle means you do L of X first, and then do L inverse of whatever the result is. But over here in matrix land, because M is the matrix representation, L of X is equal to M times X. Function evaluation is the same as matrix multiplication. And then L inverse of that means you multiply those matrices together, whatever this one is. And when you do that, the result is X. And similarly, you take M times M inverse of X, you get X. So in matrix land, here is the arithmetic, the matrix arithmetic that reflects these functions here. And this is the key to how to find it. So let's look at this variety right here. M times M inverse times X equals X. This says that the matrix M times M inverse is equal to the identity matrix, 1, 0, 0, 1. And the reason is that if you apply the identity matrix to X, you get X back. That's why it's called identity. So it says that this matrix here must be the identity matrix so that this holds. And we know how to solve this. Let's take our M to be 1, 2, 3, 4 again. 1, 2, 3, 4, we write down these known ones. M inverse is what we're looking for, so I'm going to put a big capital X there, meaning I want to solve for that. So that's my variable I want to solve for. We suppress these variables when we're solving equations, but it's incorporated in these dots. So these dots mean times X equals, like they did with linear systems, 1, 0, 0, 1. Now on the right-hand side, we don't have a single column. We have 2 columns, but it works exactly the same. When we row reduce this, we're going to get the solutions. So when we row reduce the left-hand side, we get the identity because the columns are linearly independent. And when you do row reduction on the whole thing, the right-hand side, I believe, becomes minus 2, 1, 3 halves minus 1 half. So what do we have actually on this right-hand side? This is the solution. This is X, which is the inverse. So this is why this little method of reducing this matrix by hand gives you the inverse. You're doing nothing more than solving this equation, M times X is 1, 0, 0, 1. So that's the first part of the video on inverses. I'm going to stop that here, and I'll give you a second video